The most important element in a digital transmitter is probably the digital modulator. In this video, we'll introduce the main functionality of a digital modulator and we'll see how this functionality is implemented in a practical case. The main functionality of a digital modulation is the conversion of bits, the bits containing the information that we want to transmit and that are transmitted at a given binary rate RB bits per second into a signal, a continuous time signal, an electrical signal that is appropriate taking into account the characteristics of the channel that is going to be used during the transmission. Typically, the bits are not transmitted individually, but by blocks. The binary sequence is divided in blocks of n bits, and each block of n bits is called a symbol. Therefore, we have a conversion from bits to symbol, with a symbol being just a block of n bits. Taking this into account, the alphabet for the symbols is 2 to the power the number of bits per symbol, 2 to the power n, which is denoted as capital M in this case. And its symbol will be denoted by BI, B0, B1, up to B capital N minus 1. We have bits that are converted into symbols. Binary sequence BB is converted in the symbol sequence B. Therefore, in a digital communication system, there are two transmission rates: the binary rate, bits per symbol, and the symbol rate, symbols per second, that are also called bauds. And there is a straightforward relationship between these two transmission rates, the binary rate and the symbol rate, RB and RS respectively. And this relationship is through the product with the number of bits per symbol. A very simple relationship. Bits are converted into symbols, and then a symbol will be transmitted each capital T seconds. This parameter, therefore, is the symbol time duration and is defining the symbol rate of the system. Finally, the symbols will be transmitted through the channel, will be converted into a signal, and this conversion is piecewise. Each symbol, for instance the symbol transmitted at discrete instant n, has associated a symbol interval, the interval between n times the capital T, n times the symbol time duration, and n plus 1 times this duration. This is the symbol interval for the symbol transmitted at discrete instant n. And now we are going to see how the signal is generated. We will start with the first symbol, the symbol at discrete instant 0. The corresponding symbol interval is the interval between 0 and the symbol duration t. There are m symbols, capital M symbols, in our alphabet of possible symbols, every possible block of m bits per symbol, B0, B1, up to B m minus 1. It is necessary to define a set of capital M signals, capital L M waveforms, with a support between 0 and capital T. S0, S1, up to S m minus 1. And a given symbol is associated to a specific signal. The symbol of index I is associated to the signal of index I. And when the symbol that we want to transmit is the symbol of index I, the signal in the corresponding symbol interval, in the first interval, the signal in the interval between 0 and capital T is just the signal with index I. And this mechanism is extended to the generation of the signal in every possible symbol interval. If we transmit now the symbol at discrete instant n, the corresponding symbol interval is between n times the symbol duration and n plus 1 times the symbol duration. If the symbol is the symbol of index j, the signal in this interval is the signal of index j. Of course, to have a support in the symbol interval, this signal that initially is defined in the interval between 0 and capital T must be shifted, must be delayed n times capital T seconds. Here we have a very simple example for a 480 system. We have 2 bits per symbol. This means that the alphabet is an alphabet of 4 symbols. The symbol B0, 00, B1, 01, B2, 10, B3, 11. We have 4 signals, S0, S1, S2, and S3. Each one is associated to each one of these symbols B0, B1, B2, and B3 respectively. The binary sequence to be transmitted is split in pairs of bits, because in this case we have 2 bits per symbol. The first symbol is the first pair of bits after this splitting, is 01. 01 is the symbol of index 1. Therefore, in the first symbol interval, we have the signal S1. Then the second pair of bits, the second symbol is 11. This is B3. Therefore, the signal that we have in the second symbol interval is S3. Of course, shifted, delayed to have a support in the corresponding symbol interval. In this case, from T to 2 times T. The next symbol, the next pair of bits is 10. This is B2. Therefore, the signal that is transmitted in the associated symbol interval, in the third interval, in this case, is S2, because this is the signal associated to B2. And this process is repeated symbol by symbol. The next 3 symbols are 00, 11, and 01, which are respectively B0, B3, and B1, and therefore in the last 3 intervals of this example we have S0, S3, and S1 respectively in every symbol interval, because we have B0, B3, and B1 as the symbols associated to these intervals. This is how the modulated signal S of t is generated piecewise. Symbol interval to symbol interval. Each time a symbol is considered, each time the signal associated to this symbol is shifted to the corresponding symbol interval.